In previous video, we learned about embeddings. We saw that every word, sentence or document can be converted into a vector that represents its meaning. But now a new question arises. What do we do with millions of these vectors? Can we simply store them in MySQL or Oracle or MongoDB? The answer is yes. But that doesn't mean it's a good idea. In this video, we will understand why vector databases were invented. Let's quickly recap. We learned that embeddings are vectors representing meaning. A document becomes a list of hundreds or thousands of numbers. Now imagine storing 10 million of these. Imagine Microsoft or Amazon. They have millions of documents. Every document has an embedding. So now they have millions of vectors. The next challenge is storing them. Your first thought might be, why not simply create a database table? So let's try it. Store documents ID, its text and embedding in SQL table. This actually works. You can absolutely store embeddings in MySQL. So why did vector databases become popular? The problem isn't storing. The problem is searching in that database. When a user asks a question, we need to compare the query embedding with every stored embedding in table. If we have 10 million documents, we may need to compare against 10 million vectors. This is called brute force search. We compare the query against every document. It works, but it's incredibly slow. Searching 10 documents is easy. Searching 10 million takes much longer. And as your data grows, brute force search becomes impractical. Imagine entering a library with 10 million books. You asked for a book about Java. If the librarian checks every book one by one, you will wait forever. So we need a smarter way. Now enters vector database. A vector database is designed specifically for storing and searching embeddings. It doesn't just store vectors, it organizes them so similar vectors can be found very quickly. Traditional database answer questions like find employee ID 105, whereas vector databases answer questions like find documents with similar meaning. Traditional search relies on exact words. Like here, user searches for reset password. If the words don't match, traditional search may return nothing. Whereas in semantic, similarity match. When user searched for I forgot my password, reset password guide is returned. The wording is different, but the meaning is the same. Vector databases understand semantic similarity. Imagine a map. Imagine every embedding placed on a giant map. Similar meanings are physically close together. Different meanings are farther away. Like here, dog, puppy, cat are placed together, whereas car, truck, place are far away from dog. When someone searches for puppy, the database doesn't look for the word puppy. It looks for nearby vectors. The closer two vectors are dog and cat, the more similar their meanings, the more closer vectors are. This idea is the heart of semantic search. Now, this is where vector databases become extremely fast. They don't compare against every vector. They use intelligent indexing algorithm called approximate nearest neighbor. These indices quickly locate the nearest vectors. For example, for a company, user searches for a keyword, types a question. The question becomes an embedding. The vector databases finds similar documents and those documents are returned. Today there are many vector databases, Pinecone, Milvus, Viviate, etc. Some are fully managed, others are open source. They all solve the same problem, fast similarity search. This is why every RAG system needs a vector database. The LLM itself doesn't search millions of documents. The vector database performs the search. The LLM only generates the final answer. Summarizing why not use MySQL, answer would be traditional databases are excellent for structured business data optimized for exact match queries and relational data, whereas vector databases are built for AI applications that need to search by meaning instead of exact words. They are optimized for similarity search on high dimensional embeddings, enabling semantic search at scale. Now we know where embeddings are stored, but how does the search actually happen? How does AI find the best matching document even when the wording is completely different? In next video, we will dive deep into semantic search with practical examples. Thank you for watching.